In this video, I'm going to show you how to use theoretical distributions in R in general, and then how to analyze data using an assumption that it came from normally distributed population. So let's start with theoretical distributions. So R functions for theoretical distributions. Well, for most of the theoretical distributions, R has 4 functions. 3 of them are, you already know, it's PDF, CDF, and ICDF. And the 4th function, it's a function for generating random numbers. You can think about this function as a way to get a sample, a random sample from a big population with a certain parameters. So let me describe the function. The first function is called D function. I will call it D name, where name, it's a name for a particular distribution, normal, uniform, or any others. Well, it has several arguments. First of all, it's a value, and then several arguments, several parameters of the distribution. It depends on which distribution to use. For example, for normal distribution, it's average and standard deviation. For uniform, it's minimum and maximum value, and so on. Okay, D stands for density. So this function calculates a density for any given value. So it's a PDF. Okay. Let's say for the normal distribution, the function is called dnorm. Dnorm. The name is norm. For uniform distribution, it's called dunif, uniform distribution, and so on. And this is the PDF. It's a PDF function, probability density function. The second function, it's called pname, where name is a particular name. So it also has argument x, which is a value, and then the parameters. For example, for normal distribution, it's pnorm. For uniform distribution, it's punif. And this function returns a probability. For any given value, it returns a probability to find a value below or equal to that, which is, of course, a CDF, cumulative distribution function. The third function is qnorm, x, p1, p2, and so on. And of course, it should not be x here, it should be p here, because q function is for quantiles. It finds a quantile, you give a probability, and you get a value. Okay. For example, for the normal distribution, it's qnorm. For the uniform distribution, it's qunif. And then that's ICDF. So for any given probability, it gives you a particular value. Then the 4th function is called rname. R stands for random. So it gives you a random or several random values for from a particular population. So it has argument n, and it's a number of values. So if you need 1 value, it will be 1. If you need 5 values, it will be 5. And then you also provide these parameters of the distribution. And similarly, it's rnorm if you want to get values from normally distributed population, or runif if you want to get values from uniformly distributed population. So it's random values, getting random values. Okay. Now let's let's look at these functions. We will start with PDF. And I will do all examples for both normal distribution and uniform distribution, so you can see a difference. Okay, so let's say that our normal distribution has parameters mu equal to 70, and then sigma equal to 10. Let's say we are talking about weight of people, so the average weight is 70 kilograms and standard deviation is 10. Okay. Now, if you want to make a curve, a PDF curve, you need to generate a sequence of these x values, starting from the minimum and ending with the maximum. Okay. You remember that for normal distribution, most of the values lie within 3 standard deviations of mean. So we can start with mu minus 3 sigma, we can end with mu plus 3 sigma. Okay. So we need to generate a lot of x values in between. Okay. So this is how to do that. So I generate x, I will call it x1 here. There is a function sequence that can generate anything from the one to the other values, and then you can say how many values will be in between. I will show you how to do it. Mu minus 3 times sigma, that's the smallest value. Then mu plus 3 times sigma, that's the biggest value. Okay, so the smallest value in this case will be 40. It's 70 minus 3 times 10. And the maximum value will be 100. It's 70 plus 3 times 10. But how many values in between? Well, you can specify an argument which is called length out. So it's how many values will be in between. Let's use 100. I think it's enough to get a curve. Okay. So if we run this, okay, oh, I need to run all lines here. If you run this, you see that x1, it's a sequence of 100 numbers. So let me show you the numbers here. So you can see that the first number is 40, then 40.6, and 41.2, and so on. So they are equally distanced numbers between the 40 and 100. So you can see that the last value is 100 exactly. Okay. Then we will do the same. We will use the same. Let me just call it x. We will use the same for the uniform distribution. Okay. Now we can generate the density. We can calculate density for every x value here. We will calculate two densities. One assuming that it's normally distributed, and one assuming that it's uniform distributed. Okay, so for uniform distribution, we know it's a function d name. So we write d norm because it's a normal distribution. For normal distribution, it's a function d norm, right? So d norm. Then the x values, the generated x values, because we have 100 values, it will calculate density for each of the 100 values. So in F1, we will have 100 different densities for every value. And then you'd specify the parameters, it's mu and sigma. Okay. Now, for the uniform distribution, it's d unif, also x. And now we also need to specify the parameters. In this case, it's minimum and maximum value. Let's use the same as we used for the generating the sequence. So the smallest value will be mu minus 3 times sigma, and the largest value will be mu plus 3 times sigma. Okay. So now we can make a plot. Okay. I'll start with a simple plot only for the normal distribution. So I say plot x and f1, and then the type is a scatter plot, so it's a p. Okay. So I need to run all these lines here. So that's the uniform distribution. So you can see 100 points for every generated value from x. For x from 40 to 100, we calculated a density. So this is densities, okay? So I can create a line plot instead, because it's smooth enough, we have enough points. Then, for example, use the blue color here, okay? So that's the normal distribution, okay? Now I can create the same plot for the uniform distribution. So let me call this, the main title is normal distribution. Normal distribution. Okay, I'll just copy and paste this, change f1 to f2 because that's exactly where we have densities for the uniform distribution, and then write it uniform here. Okay, so I can run these two lines. Oh, I need only one line, of course, in this case, only this one. So this is uniform distribution. You remember that in the uniform distribution, all probabilities, all densities are equal. Okay, now I'll show you a little bit more about R, in particular how to make two plots, two curves in the same plot. Okay, so I want to show the same axis and the density curve for normal distribution and density curve for uniform distribution inside this axis. So I will start with just copy and paste the normal distribution. So that's my plot for the normal distribution. Now what I want to do, I want to add lines or curve to this plot. Okay, so I don't want to make a new plot. In this case I say lines, or just line, x, f2, so I use the uniform distribution here, and then I will make it a red color, okay. I don't need the main here, so I will just change it to distributions, or PDF, and it should be lines here. It should be lines here, not just one line. So if I run these two lines, that's the result. So you can see, so this is the normal distribution, and this is a uniform distribution. The area under each curve is 1. Okay, so we can see that you have the smaller density here and the larger density here for normal distribution, but for the uniform distribution you have the same density, so the area will be the same. Okay, you can add a legend to this plot. First argument for the legend is where it should be located. I will use top right. Okay. Then you need to specify the legend itself, the normal distribution and the uniform distribution. Then you specify the colors. In this case, first is blue, and second is red. Then I will also specify the line type, which is equal to 1 for both. Okay, so if I run this, I will get a legend. So you can see that the blue curve is a normal distribution and the red curve is a uniform distribution. So this is the PDF. And we know that we use PDF only for getting an idea on how the density change during inside the interval. So what's the shape of the distribution, right?